Section 5.2 is called Verifying Trig Identities, and I'm going to show you some homework questions. First one says, fill in the blank to complete the fundamental identity. This is a very important fundamental identity. Sine squared plus cosine squared of theta will always equal to 1, and we call this as Pythagorean identity. This Pythagorean identity has second and third version. So the most famous one is, yes, sine squared of any angle plus cosine squared of any angle is equal to 1. But then if we divide everything by cosine squared x, we can get the version of tangent squared of x plus 1 is equal to 1 over cosine will be equal to secant squared x. So here 1 plus tangent squared theta is always equal to secant squared theta. For the third question, sine is an odd function. So sine of negative theta will be always equal to the negative of sine of theta, because sine x is an odd function, and all odd functions, when you change your input from x to negative x, they will generate a negative output, the opposite output of the original output. Cosine and secant of x, because secant is reciprocal of cosine, these are the only two even trigonometric functions. But secant of negative theta will be the same thing as secant of theta, because even functions, the definition of even function is, even though you change your input from x to negative x, it still generates this exact same output as f of x. For number 5, we have 2 blanks to complete. We need to find the equivalent of tangent of theta. Tangent of theta is always the reciprocal of cotangent of theta. This is called reciprocal identity. And tangent of theta is always also equal to sine of theta equals to the sine of theta divided by cosine of theta. This is called quotient property of tangent theta. And then this is called the reciprocal property of tangent theta. So number 6 is very similar to number 5, but this time it's cotangent of theta. Cotangent of theta is 1 over tangent of theta, and cotangent of theta is also equal to cosine of theta divided by sine of theta. Now, number 7 says use identities to simplify this expression. So we're going to choose the equivalent version of cosecant of x minus 1 over cosecant of x. Whenever the question is in terms of secant and cosecant, I like to change them to in terms of sine and cosine. Cosecant of x is always equal to 1 over sine of x minus, and 1 over sine of x will just return me a sine of x. So this is the expression I need to simplify. Since they don't have a common denominator, because this one has a denominator of 1, I need to multiply the second one by sine of x to get them in common denominators. So 1 will stay the same. Sine x times sine x is sine squared of x, over, and the common denominator is just now sine of x. And then using the Pythagorean identity, 1 minus sine squared x will always give me a cosine squared x. And then I'm dividing this now by sine of x. And since this answer is available in the answer choices, I will not try to simplify it further. And this is done for number 7. Number 8, we're going to simplify 10x times cotangent of x minus cosecant of x. I would like to distribute before I change them in terms of sine and cosine. So when I distribute 10x over the parentheses, I will get 10x times cosangent of x minus 10x times cosecant of x. So we know that tangent x and cotangent of x, they're reciprocal of each other. So basically, I want to keep the tangent of x, but instead of cotangent of x is always equal to 1 over tangent of x. Minus, I want to now change the tangent of x as sine x over cos x, because this is the equivalent for tangent of x. And cosecant of x is the same thing as 1 over sine of x. Now, when I see which one cancels out, the top 10x and the bottom 10x cancel out, and I'm just going to get a 1 over here. Here, the top sine x and bottom sine x will cancel out, and I will just get 1 minus cosine of x. And then I will try to put this answer first, And then if it doesn't accept this, I can just keep simplifying it further by getting them in common denominator and writing them as a one single term. So if I change the 1 as cos x over cos x first, so I can change the 1 as cos x over cos x. So the denominators will match now. So I can also rewrite this expression as cos x minus 1 over cos x. If this answer is not accepted, I will try this answer. Now for number 9, it's another simplification question. And for number 9, we want to simplify 1 over cosecant squared theta plus 1 over secant squared theta. It's totally up to you if you want to go ahead and change them to sine and cosine right away at the beginning, or you want to work with them first and then change it. My opinion is I want to go ahead and change them to sine and cosine first. So 1 over cosecant of theta is 1 over sine of theta. But because this is cosecant squared theta, so I need to actually square both of these terms. 1 squared is still 1, but sine of theta, when you square it, you get sine squared theta. Plus, similarly here, I have a 1 at the top, and secant squared theta. Secant is reciprocal of cosine. But again, because this is secant squared theta, I need to square the 1, which is still 1, and I need to square the cosine, and it becomes cosine squared theta. 1 over 1 over sine squared theta is just sine squared theta. And then 1 over cosine squared theta is just cosine squared theta. So now this is a very, very familiar identity. Sine squared theta plus cosine squared theta is always equal to a 1 for any functions, for any trig functions. For number 10, we want to simplify sine alpha minus cosine alpha to the power of 2. This means I need to multiply sine alpha minus cosine alpha by itself, because that's what the definition of square means. And then when I square them and try to simplify, sine alpha times sine alpha is sine squared alpha. Sine alpha times negative cosine alpha is negative sine alpha cos alpha. Negative cos alpha times sine alpha is negative sine alpha cos alpha. And then negative times negative is positive, and cos alpha times cos alpha is cosine squared alpha. After we expand this expression, I know that sine squared alpha and cosine squared alpha together, they will just return me a 1 because of the Pythagorean identity. And then here, these are the same things and they're both negative. So when I combine them, that's total of negative 2 sine alpha plus alpha. And then that's what I get for number 10 as an answer. For question 11, it's a similar simplification. We want to simplify this expression, and the direction says the simplified form with no quotients. And then we're going to just try to simplify this as much as we can. This one, 11 plus sine theta to the second power. You're very welcome to write them next to each other and FOIL them, but I'm going to use a shortcut. Shortcut says that I can just square the 11, which will give me 121. So 11 squared is 121. Plus, and then 11 times sine of theta is just 11 sine of theta, but I need to double them, so it gives me 22 sine of theta. Plus, sine of theta squared is just sine squared theta. That's what I get when I expand the first parenthesis. Plus, expression continues with a plus cosine squared theta. Sine squared t plus cosine squared t will always return me a 1. So 121 plus 1 is that's total of 122. And then here I'm going to get 22 sine of theta. And this is what I can get as a simplified version to number 11. For number 12, we want to factor the following trigonometric expression. So it doesn't say simplify anymore. It says factor this. When we were learning about factoring, we learned that if we need to factor something looks like a squared minus b squared, there's a formula we can use. factors will be always a plus b and a minus b. So in this case, a squared is sine squared alpha, and b squared is secant squared beta. So that means the first parentheses will be sine alpha plus secant beta, and then the second parentheses will be sine alpha minus secant beta. Since the question is only asking for factoring, I will plug this answer to my MATLAB to see if it was accepting it. If it wants further manipulation, you might have to change the secant theta to 1 over cosine of theta, get them in common denominators, but I don't think so. I think it will just accept this answer. Number 13 is another factoring. So this is another difference of two squares, a being sine x plus 1, and b is sine x minus 1. So if I apply the formula as a plus b, so I need sine x plus 1 plus sine x minus 1. Now I need a minus b, so a is sine x plus 1, and minus b is this, but because of this minus, everybody's going to change sign here. So I'm going to write negative sine x and plus 1 for the a minus b part. So when I simplify them now, sine x plus sine x is 2 sine x, and then positive 1 and negative 1 cancel out. But in the second parentheses, positive sine x and negative sine x cancel out, and I get 1 plus 1, which is just 2. And then when I multiply these two things, my answer becomes as simple as 4 sine of x for number 13. Number 14 is another simplification, and they want me to write it as a single trig function. So instead of cotangent of x, I can write its equivalent, which is cosine x over sine x. And then I'm multiplying it by sine x. So the top sine x and bottom sine x cancel out, and the answer just becomes a cosine of x for number 14. Similarly, for number 15, instead of tangent of x, I can write sine x over cos x. Instead of cotangent of x, I can write cos x over sine x. Again, this wasn't the only way to do this. I could use just, they are reciprocal of each other, and they will cancel each other anyway. And in any way, the answer will be just 1 for number 15. Number 16 is asking me to simplify this as a single trigonometric function. So I'm going to start changing everything in terms of sine and cosine. So instead of secant beta, I can write 1 over cosine of beta. And instead of tangent of beta, I can write sine beta over cos beta. And instead of cosecant beta, I can write 1 over sine beta. So when I multiply these two things at the top, 1 times sine beta is just sine beta, and the denominator is cosine beta times cosine beta, which will return me a cosine squared beta. And the denominator is, the bottom expression is 1 over sine of beta. Now I'm going to use the properties of dividing fractions. So we need to copy the first one as sine of beta over cosine squared beta. And then we're going to multiply this by the reciprocal of the bottom one. And the reciprocal of the bottom one is sine beta over 1. So sine times sine will return me as sine squared beta. And then the bottom is cosine squared beta. And sine over cosine is tangent. But if I have sine squared over cosine squared, that means I'm going to have a tangent squared of beta here. So this will return me a tangent squared of beta as a final answer for the number 16. And this finalized the homework 5.2.